What's up, everyone? Welcome to another video for AP Statistics. In this video, we're going to focus on statistics from categorical data. Keep in mind, categorical data is data that comes from a categorical variable, and that is where the answer to the question is going to put you into a category that we would typically label with a word. All right, so what are some statistics that come from categorical data? Now, let's quickly remind you what a statistic is. Statistics are values that describe data taken from a sample. So the hope is that they reflect the population parameter. As long as the sample is random, representative, and truthful, that statistic, the information from the sample, should be fairly accurate, pretty close to what is true for the population parameter. Now, the list of statistics from categorical data, again, the list of information that can be described from categorical data is actually pretty short. So number one, we have counts. These are also known as frequencies. Would be like we got a big sample of Skittles, and we counted 96 of them are green. That would be the frequency, how many greens we counted. And the second statistics would be the proportions or percentages that came from that sample. So here we would take the 96 that we counted, divided by our total, and we get the proportion. Maybe we'd find out that 18% of the Skittles are green in our sample. Now, as long as that statistic, the sample, was random, representative, and truthful, we should be able to say with pretty good confidence that 18% of all Skittles are probably green. Now listen, if our sample showed 18% that are green, it doesn't mean that the population is also guaranteed to be exactly 18%. But if that sample was random, representative, and truthful, I bet 18% is a pretty close approximation of all Skittles that are green. Now, these proportions or percentages are also known as relative frequencies because it's a count that is more relative to the whole, and that's why we like percentages there. Now, I want to talk about the case against using counts or frequencies. Now, I just listed that this is one of the statistics, but I want to make sure you understand that we typically don't use counts very often. Here's why. The goal of a sample statistic is to approximate a population parameter. So for example, if a random sample shows 88 people like chocolate ice cream, that number 88 is probably not even going to be close to the number of all people that like chocolate ice cream. Let's say your population is a couple 100,000 people and you got 88 people in your small sample that like chocolate ice cream. There's no way that the 88 is going to be even close to the number of actual people that you would count in the population that like chocolate ice cream. That number could be well into the thousands. So although it is still a statistic because it came from a sample, it's not really feasible to use it as an estimate for that true population parameter, which is why we would much rather use proportions. Because if I find out that maybe 17% of people in my sample like chocolate ice cream, then it would make sense that that 17% should be pretty close to the percentage of all people in the population that like chocolate ice cream. Again, as long as it was random, representative, and truthful. All right, so now let's actually look at some examples here so we can actually see how we do this. So in a simple random sample of 188 students was taken one morning at Beaver High School. And students were simply asked how they arrive at school. So there was one categorical variable here. How did you arrive to school? The answer that I got back was a word. It put you into the bus category, the parent category, the drove yourself category, or the walk category. Now, what we could do here is we could talk about the 90 kids. That would be a statistic. 90 kids was the frequency or the counts. I counted 90 kids that drove themselves. But again, we don't necessarily like using counts. So we'd much rather use the percentage. So we would simply say, all right, well, we would take the 90 kids that we counted that drove themselves to school, divided by the 188, and we could use our calculator, unless you're really good at math in your head, and we get 0.340 if you round that properly. And we could always move that decimal twice to get 34.0%. So again, we got a fraction, we got a proportion, we got a percentage. They're all technically the same thing. Easy, right? Now, how would we actually describe this number? How would we notate this number? Well, one thing we could do is use words. We would say our sample shows that of 188 students, 34% of them drove themselves to school. Okay, great. Using words is awesome, but a lot of times in math, we like to use symbols to notate things. So another way that we would actually notate what this number represents is using some symbols. First, we use a capital P. That capital P could stand for proportion or percentage, right? And then next to that P, in parentheses, we would write down what it is we found the proportion of. So this would be kids that self-drive themselves to school, right? So this does not mean P times self-drive. This is not function notation or anything like that. All we're trying to say is that the proportion of students in our sample that, in the parentheses, drive themselves to school is equal to 90 out of 188, 0.340, or 34.0%. So rather than using words and say 34% of all kids in my sample drive themselves to school, we could use this super cool, maybe not super cool, but this cool way to notate it. Pretty basic, pretty simple. And again, we could also say, oh, I wonder what proportion of kids walk to school. And again, notice that notation. That's all that is. And we do 34 out of 188. And you guys can grab a calculator and figure that out. Very simple. All right, let's talk about looking at some statistics from a two-way table. So we also observed from those 188 students whether or not they were tardy to their first class. So maybe we asked the teacher who was tardy and who wasn't, because if we asked the kids, they would lie, and then I don't get truthful answers. So again, just trying to cover my butt here. All right, so here's a two-way table that shows each variable. On the left, we have how they got to school, and across the top, we have were they tardy? Question mark? Yes or no. All right. So the first thing we can do is do, well, what we've actually already been doing. We could say, all right, what proportion of students ride the bus? This would be what we call a marginal distribution because it comes from the margin, the totals, right? I don't even care about tardy at this point. I didn't say tardy. I didn't say not tardy. I just said, hey, what proportion of kids ride the bus? So this would be looking at our totals. 35 kids ride the bus out of 188. Nice and simple. Grab a calculator. 35 out of 188 is 0.186. And then, of course, we can move that decimal twice to say 18.6% of the students in my sample ride the bus. Easy. And obviously, we can repeat that. We could even look at another variable about being tardy. What proportion of kids said, yes, we were tardy to our first block class? Once again, this is also considered a marginal distribution because we're just looking at our totals down here. We're not looking, I don't even care how you got to school. I purely care if they were tardy or not. And that would be 64 total kids that were tardy out of 188 students. So 64 out of 188 is 0.340 if you round that correctly. And that would be 34.0% of kids are tardy. But we could also do something what's called conditional distributions. These are looking at not on the numbers in the margins or the totals. These are looking at the numbers on the inside of the table, the 26, the 9, the 21, the 8, and so forth. So let's talk about what that would mean. So let's just say we ask this question. Amongst the kids that drive themselves to school, what percent are tardy or proportion are tardy? So again, we're still going to use that P for proportion because we're looking for a proportion. And if you heard the question, I said, amongst the kids that drive themselves to school, what proportion are tardy? So we're still looking at the proportion that are tardy, but there was a condition. Amongst the kids that drive to school, I'm only allowed to look at the kids that drive themselves to school. So to denote that in our notation here, we put a line. It's just a straight vertical line. And after that line, we put the condition, they drive themselves to school. So again, in words, this is the proportion that are tardy of the kids that drive to school. Or I could actually flip that around and say, of the kids that drive to school, what proportion are tardy? But it doesn't change the fact that I'm looking for the proportion of kids that are tardy, which is why tardy goes first. But there's this condition amongst or of that the kids have to be driving themselves to school. Now, how does this change? Well, what actually changes is my denominator because I'm only allowed to look at the 90 kids who were late to school. Well, I said that wrong. I'm sorry. I'm only allowed to look at the 90 kids who drove themselves to school. So of those 90 kids, amongst the kids that drive themselves to school, 41 of them were tardy. So again, this is called a conditional proportion because there's a condition, right? We're combining two variables at once here. Now, we're only going to get one statistic, one value, but that one value came from looking at the connection of two things. So I'll repeat the question one more time. Amongst the kids that drive to school, what proportion are tardy? So we're looking at the proportion of kids that are tardy, but after the line is our condition, which was they drove themselves to school. The condition changes the denominator because I'm now only allowed to look at the 90 kids that drive themselves to school. The 35 that ride the bus, I don't care about the 29 that come with their parent. I don't care about the 34 that walk. I don't care about it. I only care about the 90 that drive to school. And of those 90, 41 were tardy. So 41 out of 90 would be 0.456 if you round that correctly. Or again, 45.6%. Let's just do another one so you can get used to hearing another question here. Of the kids that are tardy, what proportion ride the bus? Again, listen to that one. Of the kids that are tardy, what proportion ride the bus? So I'm asking you what proportion ride the bus. The condition was of those that are tardy. So kind of switched it around a little bit there. That's why you got to really read the question. So if you're seeing this on paper, you're seeing amongst the kids that are tardy, of the kids that are tardy, what proportion ride the bus? So the question says what proportion ride the bus, but there's a condition. That's what that vertical line is for. And after the condition comes, well, what the condition is, they had to be tardy. So once again, the condition changes the denominator because I'm only allowed to look at kids that are tardy. 64 kids are tardy. Not allowed to look at the 124 because those 124 were on time. They weren't in my condition. So of those 64 kids that were tardy, 9 of them rode the bus. And again, I could divide that out. 9 divided by 64 is 0.141 or 14.1%. So again, I'm just trying to show you multiple different values that can come from this data. And what do we call values that come from a sample of data? Statistics. Again, the big thing I'm trying to get through to you in this video is that there's different notations with this P thing, but we also got to really consider the question and how we can intertwine two variables together. All right. So lots of different questions that could come out of this. So we got to really understand what the question is asking, because this can be, and I'm going to be honest with you, can be a little bit confusing if you're not really paying attention to reading the question. So let me just kind of do a couple more here just to make sure you're really reading the question, right? What if we said to you, hey, in this table here, what proportion of kids were both tardy and they drove themselves to school? So we're looking at the proportion of all the kids that were both tardy and drove themselves to school. So self-drive. Sorry for my handwriting being terrible. All right, so once again, there's no condition here. I didn't say amongst these kids or of those kids. I just said what proportion of all kids were both tardy and drive themselves to school. So this would be an and, right? So we're saying, okay, that would be 41 out of 188. The only time your denominator changes is if you have a condition of the students who drive to school, of those that are tardy, amongst these kids, amongst those kids. That's when the denominator changes. That's when you need that vertical line. But if you just see the word and, what proportion of kids are tardy and drive themselves to school, that's easy. Just look. How many kids are tardy and drive themselves to school? 41 out of 188. Divide, get your proportion, move the decimal, get your percentage. Very simple. So we can intertwine these variables in all different kinds of ways. You just have to know, what is the question asking? How do I notate it? And of course, how do I make sure I get the right answer? So really take the time to understand that when you have a two-way table, I mean, the statistics that come out of it are very limited. Counts or proportions. We tend to kind of gravitate towards proportions. But those proportions can come in all different shapes and sizes depending on what the question's asking. So really take the time to understand that, especially when you're doing some problems. All right, that's it. Hope you learned. See you later.